Um, I want to very quickly go through complete examples of solving systems of equations, characterizing them, and then solving them, how to state the solution. I'm going to do it quickly because this is in my NMath A course. It's just the mechanical aspects of it. And then I want to end up on this little series of facts. And I'll save that for the end of this video. Oops, here's two equations and three unknowns. Here's the augmented matrix without the line in it. So this right column is really this B part. We do the row operations. And actually, in this case, since there's only two, and these two rows are not just scalar multiples of each other, we already know the rank is 2. So at this point, without even doing row operations, we know the rank is 2, n is 3. So we know we're going to get infinite solutions with one free parameter. But to actually solve, we do the row reduction. This tells us, let's see, x1 plus 2x2 minus 4x3 equals 9. Anyway, we can solve. Well, that's what this equation is. x1 and x2 are the pivot variables, so x3 is the free variable. And we'll just call it t here, which can vary over the whole real line. And we solve for the pivot variables in terms of that t. So now we've got it. x1 equals 1, x2 equals 2t plus 4, and x3 just equals t. Here we have three equations and three unknowns. Just be careful. Don't always look at how they line up. This is x1 here. So it goes over here, not here. In this case, we do need to do some row ops and find out its rank is 2. Again, n is 3. So we know we're going to get infinite solutions, one free parameter. And again, x1 and x2 are the pivot variables. So x3 and x3 is the free variable. We'll just set it to t again and solve for x1 and x2 in terms of. Here's a, let's see, 4 by 4, 4 variables, 4 equations. The row reduction is kind of painful, but once you get there, you can just immediately spot it. You've got 0 equals 1, you know it's no solution. Now, let me get to this little fact. I have this product, AB. I'll put it in the AB times x equals 0, right? Well, by the associative property, I can look at that as A times BX. So anytime BX is, meaning x, if x is in the null space of B, then it's certainly in the null space of AB, because you're still going to get 0 even if you plug it into this equation. That means the rank of the product is no bigger than the rank of B itself. I guess you could say either way. And here's another equation. I'll take that product times x. I'll regroup it a little bit and redefine what bx, I'll call that y. Anyway, that all equals c. abx equals c and ay equals c. Well, any c in the column space of AB, meaning any possible c you could get from this equation, is also in the column space of A, right? Thus, the rank of the product is less than or equal to the rank of A. I had to think about that. So that the rank of a product is no bigger than the rank of either matrix in that product. And in particular, we're looking at square matrices. What that is going to mean is if either A or B or both are singular, and so is their product. We now have that little fact to put in our pocket. And I'll stop there. We're almost done with this part of it, the basic linear algebra. I do want to cover generalized vector spaces before, but anyway, I'll save that for another video.